Well, good morning. It's 8:12. Sorry, I've had trouble getting in this morning. I hope that hasn't discouraged y'all from hanging around. But um, first, my internet wouldn't come on. I thought it was Zoom because I was sitting there watching Zoom try to open for like 3 minutes and nothing happened. Then I happened to notice down were my internet lines and they weren't open. So that was the problem. It wasn't Zoom's fault, it was the internet fault. And then I couldn't get the internet to open, so I had to shut everything down, bring it back up, and then it came up on a wrong internet, so I had to change back to the correct one. And then, of course, Windows Teams had to come up and had to shut that down because that is just always in the way. So finally I got everything up, but I haven't been able to locate a student yet. So I hope you are coming, that you haven't given up, because it took at least 10 minutes to work all that stuff out. And so on the premise concept that y'all are going to show up this morning, somebody will. Oh, and here is James. Fantastic. Fantastic. Let me get James marked present. All right. Welcome, James. Glad you're here. Okay. Had you tried to get in earlier? I'm so sorry. I was trying to get in myself, and I thought Zoom was failing because I sat here watching the Zoom thing go in circle for at least 3 minutes. Think, what in the world is going on here? Of course, with all the news and the elections and stuff, I figured, well, the whole internet must be buzzing as people are trying to get their news feed before they head off to work. And then I happened to glance down and found out I had no internet. Okay, and I don't know why I had no internet. So anyway, Zoom was trying to load when it couldn't get an internet signal. So I worked on the internet for a while and then realized that Zoom was interfering with that because it was a mess. So I finally had to shut my entire system down and bring it back up from scratch. So it's been quite a morning. So that took at least 10 minutes for me to work all that stuff out, taking everything down, bringing it back up, and then it brought up on the wrong internet, so I had to get that corrected. So finally, we're here. Sorry about this, but anyway, let's get going. Any questions, issues, concerns? Okay, because I had already started. Yes. Okay, you're what? Okay, I still couldn't quite understand the first part. My hearing's so bad. Oh, to turn things in? Just get them to me when you can, as soon as you can. That'll be fine. I just don't want you having lots of multiple things out there. Okay, try to get them in as soon as you can. I don't put deadlines on things too much, but I also don't want you to get yourself into a cram situation where you have too much going on. So just get them to me when you can, as fast as you can. I'm doing the same thing with grading. I'm way behind on that. In fact, I printed one of your papers just recently. Which one was this? Uh, Cal 3, your Cal 3 research paper. I printed that, and lo and behold, the my printer, first time it's ever done this, it ripped part of the page, but I got it all out. But I had to dig into the printer to find that corner that was missing. And sure enough, because it prints on both sides, and when it fed back in the second side, it must have put something in crooked. So anyway, so I'm trying to catch up on grading as well as I'm sure you're trying to catch up on work. So I know the feeling. So we'll sludge through it somehow. All right. Any other? Okay, great. All right, super. All right, any other issues or concerns? Okay. Now I think where we left off last time, I'm already recording so I don't have to start that over again. Where we left off last time was we had done example 4 at the bottom of page 137, chapter 3, determinants, 3.4, applications of determinants, and we're using Kramer's rule, and I'm going to try to reproduce what we did in example 4 as quickly as possible. Okay, so here was example 4, minus x, and somehow it's turned out red. I'm going to go back to black. I guess it was something I was doing in lab. Wait a minute, James, you're already here. It must have kicked you out and brought you back, but it looks like somebody else is trying to get in too. Oh, that's you twice. Okay, you're trying to increase the enrollment, aren't you? Okay, James, I've got you in twice now, but it's okay with me. I don't mind having you here twice. Okay, but can you hear me? James, can you hear me? Okay, good. Okay, all right. Okay, so example 4, bottom of page 137, minus x plus 2y minus 3z, the pen is not writing well today, is equal to 1. 2x plus z is equal to 0, and 3x minus 4y plus 4z is equal to 2. Okay. Now, all it asked for in the first part was solve the system of linear equations for x. Okay, I'm going to try to do that real quickly now. What x would be then would be the determinant. I like to start with the denominator because that's your determinant of your coefficient matrix, minus x minus 1. You only put numbers down there. Okay, minus 1, 2, minus 3, 2, 0, 1, 3, negative 4, 4. Okay, that's your denominator. I probably didn't leave room enough for the numerator here. So for the numerator, instead of the x coefficients, we put the constants here. So if I can squeeze them in here, that would be a 1, 0, 2 there, and then the rest of them are the same. 2, negative 3, 0, 1, and negative 4, 4. I don't quite have enough room, but I'll squeeze it in. Okay, now we work that out. For that denominator matrix determinant, let's go on and do our expansion. Negative 1, 2, negative 3, negative 1, 2. 2, 0, 1, 2, 0. And 3, negative 4, 4, 3, negative 4. Okay, let's do that one. That first down diagonal gives you a 0. The next one gives you a 6. So this isn't actually right nomenclature to put the bars there, but I'm doing it. 6. And then here we have a 24, I believe it is, plus 24. And then your up diagonals would be 0. And then this would be a minus 4. And the last one would be a minus 16. Okay, So that's a 30 on this side and a minus 20 on this side. So this gives you a 10. And that's what they got in the book also. Okay. Now, this determinant up here, far better to use goodness, I can't think of the term now. It's the C word. And anyway, we're going to eliminate this column and that row, okay? And we're using this position, which happens to be a negative, plus, minus, plus, minus. So that's going to be a minus 1 times, and then we'll do the determinant of what's left. Minus 4 is minus 8. Okay, easy to do that. Cofactors, okay, expansion of cofactors, because you had that 2 zeros and just a 1 there. That made it really easy to do your cofactors. So this is a positive 8, and you take the 8 and put it over the 10, and that gave us 4/5. So that's what your x is. Now, the rest is sort of a little easier, okay? We've already got our denominator. We don't have to do that one again. So what's in the numerator for your y? Okay, so let's just do the y numerator here. And that's going to be, you use the coefficient matrix, except where you have your y, you put your constants. So that's going to be a minus 1, 1, negative 3. Okay, this minus 1, that 1, this minus 3. The next one is going to be a 2, and then you use the 0 here, not the 0 there, different zeros now. Okay, 0, 1. Okay, and then the third one would be 3 from here, 2 from there, and 4 from there. Okay, and we'll do it, take that determinant. Now here again, I think I'll just erase what I just drew, okay, and do an expansion here. Okay, so that's going to be a minus 1, 2, 3, and a 1, 0, 2. Okay, I think it'll be easier to do this. This again gives you a 0. This gives you a 3. This gives you a minus 12. Okay, the up diagonals give you a 0, and then that's a plus 2 and a minus 8. Okay, so that's going to be a minus 20 and a plus 5. That will be a minus 15. Your denominator was 10, so your y is equal to minus 15 over 10, which is minus 3/2. Yeah, minus 3/2. Got it. Okay. Now, I don't have a lot of room left, but let's try to get our z done. Our denominator is already done for us. We don't have to do that again. So the numerator for z, and this is just the numerator for z, I'm not writing it very nicely. Okay, we'll do the coefficient matrix. The only thing is we'll put the constants here. If I can find my pen, there it is. Okay, the constants here instead of the z coefficients. So that's going to be a minus 1, 2, 1, a 2, 0, 0, that works out nicely, and a 3, if I could get the pen to show up, 3 minus 4, 2. Okay, and now this one, let's do a expansion, because you have a row here with 2 zeros in it. So we're going to wipe out this row. Cofactor expansion is what I mean. Wipe out that column, and this 2 is in a negative position. That's a plus minus, So this is going to be a negative 2 times the determinant that's left. And that's going to be a 4 plus 4 would be 8. Okay? So this is going to be minus 16. So your z is going to be minus 16 over 10, which would be a minus 8/5. And that's what the little remark says at the side of the page on page 137, very lower left corner. Apply Cramer's rule to solve for y and z. You see that the solution is y is equal to minus 3/2, z is equal to minus 8/5. Do you see how that works? All right. I hope that means yes. Okay. Now, the next application, first application was finding the adjoint of a matrix. And why would we even be interested in that? Because you can also find the inverse of a matrix using an adjoint. So that's one application of determinants. It's a long, roundabout way of doing it, but it certainly works. Then there was Cramer's rule, which is another way to solve a system of linear equations. Okay, and that works pretty nicely. Is it any shorter than Gauss elimination or Gauss-Jordan elimination? I don't think so. But it does have some advantages. Okay, and then the third application that we're going to hit in 3.4 is area, volumes, and equations of lines and planes. Now, if you notice, that's a lot of words there. That's a lot of different applications. Okay, so here's going to be the first one, and I'm going to clear the slide. Do you need that up here lit any longer? Yay or nay? No? Okay, I'm going to clear the drawings. All right. Determinants have many applications in analytic geometry. One application is finding the area of a triangle in the XY plane. Now this isn't any old triangle, okay? It can't be a triangle in space, okay, where you have the XYZ space. It won't work there, okay? But it will work if you're in a plane, okay? In the XY plane, not any XYZ, okay, but XY plane, okay? And here's how it works. If you have the three vertices of a triangle in the XY plane only, okay, and let's name them like the book does, X1, Y1, X2, that's supposed to be a 2, Y2, X3, Y3. Now, there is a little caveat here. These three vertices cannot be collinear. They have to be 3 points that are not on the same line, making the vertices of a triangle. Okay, they didn't specifically say that, but you have to. You have to have them non-collinear. Now, how in the world do you get the area of a triangle with this? Okay, here's how. I think I'll write it down here. The area of that triangle, I'll put a T down here, is equal to, now, and this seems a little strange, but there's a reason for it, plus or minus 1/2. Okay, plus or minus 1/2, the determinant that you have when you put these 3 points in a very specific determinant here. You put X1, Y1, 1, X2, Y2, 1, X3, Y3. These are the coordinates for those three vertices. 1. Now you see if if two of those were collinear, this determinant would be 0. And that makes sense, because if these are on the same line, then you have no area. Okay, so that's the area of a triangle. Okay, now why the plus or minus sign? Well, the plus or minus sign is a determinant may be negative. Areas can't be negative. So if the determinant turns out negative, then use the minus sign. Okay, if the determinant turns out positive, use the plus sign. So your area is always positive. Now you might also ask yourself, why is the 1/2 in there? And they do give a pretty nice little description here. It's a proof, and I'm going to try to do that too. Okay, I'm not going to carry it out probably in as gory a detail as they do. Somewhere here my cursor, there it is. Okay, so it doesn't have to be in the first quadrant, but I'm going to put it in the first quadrant because they did. And it doesn't have to be in this order, but I'll do it in this order. X1, Y1. Okay, that's that point right there. Up here, I think they call it X2, or is that X3? That's X3. So we'll put the X2 over here because they did. Okay, this will be X2, Y2. Okay, and then somewhere up here, they'll put the X3. I keep missing that. Y3. Okay, that forms the triangle. Notice they can't be collinear points, otherwise you have a area of 0. All right, now here's what we're going to do. We're going to note something here. If you use X1, Y1, X1, Y1, and X2, Y2, that forms a trapezoid here. Okay, so let's call this trapezoid 1, 2. Okay, and what's the area of that trapezoid? That is how you do the area of a trapezoid is flip it around the diagonal side here, and this side moves over here, this little side moves up here. These two lengths are the same. That forms a rectangle. Okay, I don't know if you can tell by my moving pen here. And the area of the rectangle is the difference in your x's here. That's x2 minus x1, and that's the base of that rectangle. The height of the rectangle is the sum of the y1 plus y2. Okay, so the difference of the x's, that's the length here. The height is the sum of the y's, which is that there, but then you take half of it because you've doubled the side of that trapezoid by flipping it over here. So that's where the 1/2 comes from, basically. Sorta. We're not finished yet. Okay, next thing we're going to do is take 1 and 3. That forms a trapezoid. Okay, same one here, a different here. Your base down here, I think I'll do this in a different color. Do you have a preference on color? We have lavender, red, pink, some sort of rusty red, yellow, orange, brown, dark green, light green, middle green, light green, light blue, middle blue, and dark blue. Do you have a preference? Let's just go with red. Okay, I couldn't hear you answer, so let's go with red. So this trapezoid here, okay, again, its base down here is x3 minus x1. And the pen is not writing well at all, and it's doing all sorts of stupid things here. Okay, and its height, when you double that, that's going to be y1 plus y3. But then you take 1/2 of it because you flipped it across the top here and doubled it. Okay, so that's that area. We have one more area to fiddle with here, and I think I'll go back to my black and point out to you, this is the black area here. Okay, this one down here. So let's go to a different color here, and let's see, what do you want? Maybe a brown? Would that show up? Or maybe an orange? Let's do an orange. Here is the other trapezoid you have. Okay, that would be this one right here. Okay, well, that trapezoid, the base is x2 minus x3, and the pen is not writing well. Okay, that's the difference between here and here. And then your height is going to be your y2 plus y3, but then you take 1/2 of that as well. Okay, now, so what we do here is add these two together, the red and the orange, subtract off the black. That gives you the area of the triangle. Okay, now they go into gory detail about that, but you add these two, you can factor out the 1/2, and when you add these two together and then subtract off the black, you wind up with exactly the same combination that you have by taking a determinant. Now, I'm not going to show all that. You can work it through if you'd like. They show you in gory detail here what you got. Okay, so let's actually do an example with it. Example 5. So I'm going to come up here and clear the screen. Do you need that up there a little longer? Are you okay with it? Okay, I'm going to clear the screen. Here's example 5, page 138. Okay, find the area. I'm going to go back to black if that's okay. They show up a little better on the screen. Okay, find the area of the triangle whose 3 vertices are 1, 1, 2, 2, and 4, 3. Now, if that had been a 4, 4 or a 3, 3, I'd have said, hang it up, Jack, because that's going to be all on the same line. These are not on the same line. Okay? So what we do is do the area of the triangle formed from that is going to be plus or minus the determinant of those points. 1, 1, 1. 2, 2, 1. 4, 3, 1. Okay? Now, no zeros in there, so let's just expand. Oops, oops, oops. You let me get away with it. Plus or minus 1/2. I forgot my 1/2 there. Repeat the first 2 columns. 1, 2, 4, 1, 2, 3. Okay, and now we'll do our determinant there. The first down diagonal gives you a 2, so this is a plus or minus 1/2 of 2. Second down diagonal is a plus 4. Third down diagonal is a plus 6. First up diagonal is a -8. Second up diagonal is a -3. And the third up diagonal is a -2. Okay, so what does that give you? Plus or minus 1/2 of, now let's add the positives together. There's a 10, there's a -10. It looks like a -1 is left. So what's your area? 1/2. Okay, because you take the minus sign because of that, and it gives you -1/2. Well, the determinant is a -1/2, so the triangle is a 1/2 square unit. Now, why in the world did they, in the top part, give us the plus or minus and then in the example ignore it? I don't know. I like the way we did it. So the 1/2 square unit. Now, they point out, they did it a different way than me. They said, what if you had 0, 1 as that first point rather than 1, 1? Then those 3 points would have been collinear and your determinant would have been 0. Okay? Now, you might say, oh, that's a bad thing to have that being 0. Well, it's sort of a good thing, because this gives you a test to see if 3 points are collinear. Do this very same thing that we did for an area of a triangle, except find its determinant, and if that determinant comes out being 0, you know these are collinear points. So here is another test that's sort of related, but a different situation from the other. And you don't need the plus or minus 1/2 on it. You don't care. All you're doing now is testing for collinearity of points. If the determinant is 0, they're collinear. If it's not 0, they're not. If they're not collinear, then you could use the plus or minus 1/2 and find the area of the triangle form. So here is the second. I think I'll go on and clear my screen here. It's easier to do here. Now I've got a sneeze, I'm afraid, so sorry about that. Sorry. I moved the microphone, but it probably wasn't enough. Sorry about that. But it woke you up, didn't it? Okay. Okay. Hold on. I don't know why they come up like that, but they do. Okay. So here is the test for collinear points in the XY plane. 3 points. Where are they? Here we go. X1, Y1, X2, Y2, and X3, Y3. Are collinear if and only if, that's the shorthand notation for if and only if, the determinant of x1, y1, 1, x2, y2, 2, and x3, y3. Wait, that's a 1 there. Those are 1s. All 3 are 1s. I get carried away sometimes with my notation there. Okay. If that determinant is 0. If that determinant is not 0, nope, not going to be collinear. If they're just a little off, you're going to have a very small determinant like we had before, 1/2, or it actually turned out to be -1/2. But then, no, actually it was just 1. The determinant was 1. minus 1 actually, which meant that did have an area. Okay, but if they're collinear, it's got to be 0. Okay, now guess what? Because of that, if they are collinear and equal to 0, then this gives you the equation of a line in effect. Okay, and here's what you do then. Well, let me back off. If you have 2 points in the plane, in the xy plane, you know they got to be on a straight line. Okay, you know they got to. Any 2 points in the plane have got to be on a line. Okay, there is one line that goes through any 2 points. Okay, now an equation for a line has an x and a y in it. So here's what you do to get an equation of a line passing through 2 distinct points. Now here they say distinct. Why do they say that? They cannot be the same point. Okay, they've got to be 2 different points, x1, y1, and x2, y2. Okay, 2 different points, and here's how you get the equation of a line passing through the 2 points. Okay, your determinant almost looks the same. Here's the difference. The top row is x, y, 1. Okay, those are your variables, x, y, and the number 1. And then you do x1, y1, 1, and x2, y2, 1. Okay, and set that equal to 0. And then you've got your equation of a line. Okay, and that would be, this is just a point, y1, that's a value. This is the variable x. So you would have y1 x, well, you'd have to do your expansion. So let's do it with actually the example. Let's not try to work it out separately. So let's go to our scale up here and clear the drawing, and we'll do example 6. Okay. Alright, find the equation of a line passing through these 2 points. Okay. Where is the pen? There it is. Okay, here's the 2 points. 2, 4 and -1, 3. Now, you can look at those and tell they're not the same points. Okay, so you want the equation of the line passing through that, so you know that's going to be the determinant of x, y, 1, then 2, 4, 1. Sorry, I've got runny nose now, all that sneezing. -1, 3, 1. Repeat the first 2 columns, x, y, 2, 4, -1, 3. Now that's not really a determinant, but you know what I mean by that. So what you get here is 4x minus y plus 6. That's your down diagonals. Your up diagonals are going to be, that would have been a -4, but because it's going up, that makes it a +4. Okay, next up diagonal, -3x. I'm going to write this one down here. I should have written the 4 over there. And this would be a -2y. Okay, and if I'd have written the +4 down here, that would have been better. Okay, so what do you get? X minus 3y. Oh, this thing is equal to 0. That's meaning they're on the same line. Plus 10 is equal to 0. Okay, I prefer writing that as x minus 3y is equal to -10. Now, Here's the test. See if you got it right. Plug in these values. 2 minus 12, that's minus 3 times 4. That would be 2 minus 12 is minus 10. Yes, that works. And then minus 1 minus 3 times 3, that would be minus 9, minus 1 minus 9, that's 10, minus 10. Yep, that's the equation that contains that's the equation of a line containing those 2 points. Does that make sense? All right, so all sorts of funny, unusual places that you can use determinants. Who would have thought finding the equation of a line between 2 points? Of course, we have other ways to do this. The double point formula. Okay, first calculate the slope between those 2 points, and then use that slope in one of the points in a point slope formula and come up with the equation. Guess what? This is just about as easy, maybe easier. Okay, because all your calculations are pretty simple. Now, remember we said let's see how we're doing on time. Yeah, we got some time. If you have a triangle in a plane, you can determine the area of that triangle. Well, now let's go to space and have 4 points in the space, not all in the same plane, and certainly not all on the same line. 4 points in space, not in the same plane. That forms what we call a tetrahedron, a four-sided figure. It doesn't have to be a regular tetrahedron. Four-sided figure, every side is a triangle, okay, as shown in your book if you happen to have your book open. Okay, you can find the volume of that tetrahedron. I'm going to clear the screen unless you need it there a little bit longer. Okay, I'm going to do here. Here is the volume of a tetrahedron. So what if you have the 4 vertices of a tetrahedron in space? Okay, that's going to be x1, y1, z1. That's 1 point. Another point will be x2, y2, z2. Another point will be x3, y3, z3. And the fourth point would be x4, y4, z4. Now, these have to be, of course, 4 distinctly different points. You can't have any 2 of them being the same. Okay, got that. They also can't be in the same plane. Okay, nor can they be along the same line, which will, of course, also be in the same plane. Okay, so they have to be 4 distinctly different points, non-coplanar. Okay, now, it gets a little more complicated, but not too much. The volume, yuck, where did that come from? Okay. All right. The volume of that tetrahedron, that's not a triangle anymore, that's the volume of a tetrahedron, is equal to, and guess what? You still got your half to plus or minus, because the determinant can be either positive or negative. Okay? But it's not 1/6 anymore, 1/2 anymore, it's 1/6. And now I'm not about to go into the proof of this one. That would be way, way, way too complicated. 1/6, the determinant of basically these 4 points. So what are they? X sub 1, Y sub 1, Z sub 1, 1. X sub 2, Y sub 2, Z sub 2, 1. X sub 3, Y sub 3, z sub 3, 1. X sub 4, y sub 4. Can't get the pen to write. Z sub 4, 1. Okay, that determinant. Now here's the bad news, folks. You can't do your expansion like you can with a 3 by 3. So this is going to take a little more work, a little more effort, but you have to do cofactor expansion. Bad news, but it's doable. Okay. Now the question is, yes, I think we have enough time to do example 7. All right, so let me clear the screen and let's do example 7. Find the volume of the tetrahedron in figure 3.3, and they give the values for those 4 points. Okay, and it doesn't matter what order you give them. Remember, if you're doing the determinant and you give a different exchange rows, you just change the signs. It doesn't change the value, but you got your plus or minus out there to take care of minus signs. So here are the 4 points. I'm going to start at the top. It doesn't matter where you start. 2, 2, 5. Okay, there's the first point. 1 on the left, thank you very much, is a 4, 0, 0. You'll see why I'm happy on that later. You probably already see why I'm happy on that. The next point is going to be a 3, 5, 2. And it doesn't really matter which one you put it. Okay? And the fourth point is going to be a 0, 4, 1. 0, 4, 1. Okay, I hope I got them all right. Okay, this is definitely not a regular tetrahedron. I mean, these sides or these points are not regularly spaced. But according to the drawing, they're not coplanar. Coming a little close, but they're not there. So what's the volume of that tetrahedron? Well, that T stands for tetrahedron. That's equal to plus or minus 1/6 times this determinant. 2, 2, 5, 1. 4, 0, 0, 1. 3, 5, 2, 1. 0, 4, 1, 1. All right. Messy, right? However, you got one row here with 2 zeros in it. Okay, so let's use that one. So let's wipe out the first column and the second row. Okay, so this is going to be plus or minus now 1/6. That's in there. Okay, now first thing we do is determine the sign of this position, plus minus. So that's going to be a minus 4. Okay, times the determinant that's left over by wiping out that row. Okay, well, that's going to be our good old favorite 3 by 3. Okay, so let's do that one here. A 2, 5, 1, 2, 5, repeating the first 2 rows. A 5, 2, 1, 5, 2, and a 4, 1, 1, 4, 1. Okay, now that would be doing that one. We still got to do this one over here, so I'm going to delete, erase, if I can get my pen to show up somewhere. There it is. Okay, wipe out this wipeout and put in this wipeout. Okay, now we got to figure out the sign of this position. Plus, minus, plus, minus, plus. So that's going to be a plus 1. So I'm not even going to write that. Well, yeah, plus 1 times. By the way, this 1/6 is times the whole thing here. So that determinant that's left over is a 2, 2, 5, 2, 2, and this is a 3, 5, 2, 3, 5, and this is a 0, 4, 1, 0, 4. Okay, now, and that's going to close. Where did you go? There we go. Okay, that's the things that are multiplied. So let's do those. Okay, let's do. Not forget, we got a plus or minus 1/6 out front. Okay, and then you got a -4 here from that one there, remember? All right, now let's do our down diagonals here, and that's going to be a 4 plus 20 and plus 5. Now let's do the up diagonals. -8 -2 and a -25. That's what you get from having everything in the first quadrant. They're all positive, so these three are positive, those three are negative. So let's see what we've got. A 20 plus 5 is 25, and a -25. Those add to 0. This is a -10 plus 4 would be a -6 times well, yeah, let's hang on to that. Plus or minus 1/6 times -4 times a -6 is a plus 24. Okay, -6 plus 4 is, -10 plus 4 is -6 times a -4 is positive 24. Okay, and then we've got to add to that. Let's do this down diagonal. It was a plus 1 in front, remember. That's a plus 10 okay, plus 0. I like that one. Oh, and this is a plus 60. Okay, here's a 0 again. This is a minus 16, and this is a minus 6. Okay, now I'm going to do these separately here. That's 70 minus 22. Okay, wow, this has turned out to be a big number. 70 minus 22 is 48, I believe it is. So this is a plus 48. Alright. 48 and 24 are 72, and 1/6 of that, and we'll do the plus sign, is 12. So I think that is our. Now they used different points and came up with a minus 12. It doesn't matter. Okay, what order you use them. We use the plus 1/6, they use the minus 1/6. So the volume of that tetrahedron is 12 cubic units. Does that make sense? Now, I don't know another way to do a volume of a tetrahedron, especially a non-regular tetrahedron. So this comes in really handy if you ever needed to know that. Determinants help you do that. Applications of determinants. Okay. Now, remember what the requirement was there. These 4 points cannot be coplanar. Well, if they were coplanar, that determinant is going to be 0. Well, guess what, team? That's not a bad thing. That gives you a way to test to see if a 4 points are coplanar or not. So let's do this quickly if we can. Clear the screen, and here will be your another application. Here's a test for coplanar points in space. I kind of wish I'd have left some of that up there. Well, no, that was from a couple slides back. So let's say we have 4 points, x1, y1, that's supposed to be a 1, z1, x2, y2, z2, x3, y3, z3, and x4. It's supposed to be an x4, y4, z4. Now, what if those 4 points there, you're trying to test to see if they are all in the same plane or not? Well, if they are 4 points that are coplanar, if and only if, so these 4 points are coplanar if and only if the determinant, and you don't need a plus or minus 1/6 in front, just the determinant of x1, y1, z1, 1, x2, y2, z2, 1, x3, y3, z3, 1, and x4, y4, z4, 1. If that determinant is equal to 0. If that's true, those are coplanar points. If those are coplanar points, that's got to be true. If and only if. If it's not, you take plus or minus 1/6 of that and you get the volume of the tetrahedron formed by these 4 non-coplanar points. Okay? Now, how are we doing? Yeah, we got 5 more minutes, so let's see the next application. If these 4 points are coplanar, okay? Well, what if you only had 3 points? 3 points are going to form a plane. If you have any 3 points in space, there, that forms a plane, okay? Now, to form an equation of a plane, you have to have variables, x, y, and z, okay? So, this next application builds on this one a little bit, okay? I'm going to clear the screen here. And if you have 3 points, okay, now these 3 points cannot be collinear, but they will be coplanar, okay? So if you have 3 points and you want the equation of the plane, here's what you got. So here's your 3 points, x1, y1, z1, x2, that's supposed to be a 2, y2, suddenly, James, did I lose you? Because I've got my picture back up there, not yours. Well, even if I did lose you, I'll keep recording because I am recording the class, and it won't go much longer. X2, Y2, Z2, and X3, Y3, Z3. Okay, that's 3 points. Okay, to get an equation of the plane formed by these three non-collinear points, here's what you do. You get that determinant that we've just been dealing with, and that would be x1, y1, z1, 1. No, I'm sorry. I got carried away here. X, Y, Z, 1. Those are your variables, okay? Then you put your points, x1, y1, z1, 1, x2, y2, z2, 1, and x3, y3, x3, y3, z3, 1. Okay, and set it equal to 0, because that then will make them coplanar. Okay, do the determinant and set it that way. Now that gets us up to 1 minute until time we're supposed to quit. Let's see if we can get that example 8 done in that minute. Okay, I know that's not going to be easy to do, but I was late getting started because of computer glitches. My internet wouldn't come up. So let's find the equation of a plane passing through these 3 points, 0, 1, 0. I like that one. -1, 3, 2. And the third point, -2, 0, 1. Okay, so it says find the equation of a plane passing through those 3 points. Well, obviously the determinant of that thing will and the matrix would be x, y, z, 1, and then the 3 points, 0, 1, 0, 1, then -1, 3, 2, 1, then -2, 0, 1, 1, and set that determinant equal to 0. Now again here I would say let's pick the row or column with the most zeros, and that would be row 2. You got 2 zeros already there. Alright, so let's start with this one, and this position is a plus position, so that's just going to be 1. So that determinant is going to be 1 times x, z, 1, xz. Okay, -1, 2, 1, -1, 2, -2, 1, 1, -2, 1. Okay, that's going to be the first one. And then we've got to move over here to this column. So let's erase. This is so easy to do when you have a magic pen. That one. And let's figure out what we've got there. Okay, again, plus, minus, plus, minus, plus. So it's going to be a +1. So this is going to be plus. And then what determinant do we have left? X, Y, Z, X, Y, -1, 3, 2, -1, 3, -2, 0, 1, -2, 0. Okay, we'll do the expansion there. Okay, both of those happen to be +1, so we're in pretty good shape here, I think. Let's see what we've got. And this has to be equal to 0. That sum has to be equal to 0. So let's do our first down diagonal. That's going to be a 2x. Our second down diagonal is going to be a -2z. Our third down diagonal is going to be a -1. Our first up diagonal, that is a little messy, so I think I will, if I can, erase that. Okay, and do our first up diagonal is going to be a +4. Okay, second up diagonal is going to be a -x. Okay, third up diagonal is going to be a +z. Okay, now why not just continue the way we just did? Our main diagonal here, down diagonal here, is going to be a +3x. The next one here is going to be a -4y. The third one's going to be 0. Okay, I think I will erase those because they do get hard to read. Look at that pain in the neck. Okay, first up diagonal here is going to be a +6z. Okay, next up diagonal is going to be a 0, and the next one is going to be a +y. Where are you? There you are, +y. Okay, you get no numbers out of this one. You get all letters, okay, now, or variables. So let's combine them together. This gives you a 5x minus x, that would be a 4x, minus 3y, that's plus 7z minus 2z would be plus 5z, and then it would be a plus 3 equals 0. I like to write that as equal to a minus 3. You could do it the other way. Let's see what they got. 4x minus 3y plus 5z minus 3 equals 0. Way to go, team. Okay, even though I have no team left. Okay, there's a linear algebra applied, and this is a pretty interesting one. Okay, in 2014, the European Space Agency Rosetta orbiting spacecraft actually landed the probe Philae, I don't know how you pronounce that, on the surface of a comet. Okay, and that has a really difficult name. They orbit the sun, but in very, very, very elliptical orbits, and they follow Kepler's first law of planetary motion, and they did the calculations linear using linear algebra, and basically that helped them in their pursuit. We did finish, believe it or not, 3.4. So the homework exercises here would be any of the odds 1 through 7, any of the odds 9 through 20. They're all at calcchat.com. Okay? Any of the odds 9 through 21, any of the odds either 23 or 25, 27, all at calcchat. Okay? 29 or 31, both at calcchat. 33 or 35, both at calcchat. 37 or 39, both at calcchat. 41 to 45, all at calcchat. 47 to 51, all at calcchat. 53 to 57, all at calcchat. 59 should be at calcchat. 61 should be at calcchat. 63 should be at calcchat. 65 at calcchat, and 67 or 69 both at calcchat. Now that also finishes chapter 3. So if you want a few more exercises to play with, you have any of the odds 1 through 17 should all be at calcchat. 19 or 21 should be at calcchat. 23 should be at calcchat. 25 should be at calcchat. 27 at calcchat. Either 29 or 31 should be at calcchat. 33 or 35 should be at calcchat. 37 to 41 should be at, or 41 should, no, through 41 should be at calcchat. 43 through 47 should be at calcchat. 49 to 53 should be at calcchat. 55 through or 57 should be at calcchat. 59 should be at calcchat. 61 or 63 should be at calcchat. 65 should be at calcchat. 67, 69, 71, 73, and either 75 or 77. Those are true false, should be at calcchat. They do have a little project here, stochastic matrices. You'll see that term show up in another place or two. You hear it a lot in chemistry, but here they talk about consumer preferences. So economics or marketing or things like this, you would also use stochastic matrices. Then they also have a thing on the Cayley-Hamilton theory, and I think we've already run into both of those gentlemen, but you can certainly write on either one of them or the combination theory, how they came about it, and that type of thing. Now, there is a 1 through 3 cumulative test. If you're interested in working those odd number exercises are also in the back. I would just focus on the ones for chapter 3, and that would be beginning at I think number 19, because I think the odd number exercises they have answers at calcchat. So basically 19 through well, they're sort of mixed up. So I know 19, 21, well, I'll let you figure them out. I know 19 and 21 would certainly work. Okay, beginning on Tuesday, we will start chapter 4. Now, I don't know for certain if I'm going to have a chance to post the third test today, because we've got to leave town today, and I don't know how soon my wife is wanting to get on the road, and where we're going to be has really lousy internet, so I won't know if I'll be able to do that. So it may be Monday, well, maybe Sunday night or Monday morning before I get to post the chapter 3 test. But you'll have it out there, plenty of time to work on. It's a pretty easy test, by the way, because I thought chapter 3 was a pretty easy chapter. Now, I know I'm talking to myself here. Nobody else, I don't think, is online now. But if you do have any questions, feel free to get in touch with me. Okay? Take care. Thanks for agreeing to make up that time. I felt bad my appointment knocked out class, but I appreciate the fact that you wanted to make it up. So here it is. I'll end the recording really soon. Take care. Have a safe weekend. Bye-bye.